Okay, so I wanted to continue today's lecture on optimization with more than one choice variable. And in fact, now I want to talk about the case where there's more than two choice variables. So there's three or more choice variables in an economic problem. You can still have this. Two is sort of the bare minimum that you need to have trade-offs. Or should I get more X or more Y? And what's the trade-off? Or should I, I'm maximizing price and quantity. I can choose my price and I can choose my quantity. And together it becomes an interesting problem. You need two choice variables for that. But there's plenty of times you might want to talk about what happens with three or more choice variables in an economic problem. So I'd just like you to have some experience with this before you move on from my class and go out into the world of economics. Okay. The first thing to know is that first order conditions are exactly the same. In other words, you set the partial derivative of the objective function. Right, if I do this, let's see if I can get a full screen. There, I think it's full screen. Still looks good to you guys, right? So for, let's say the choice variables are x, y, and z. Of course, the first order conditions are the partial derivative of f with respect to x is 0, partial derivative of f with respect to y is 0, partial derivative of f with respect to z is 0. So you have three first order conditions in this case. You might ask, well, what about the second order conditions? Remember, the second order conditions were this thing where you had fxx negative or positive, depending on whether it's max or min. And you had determinant of h is positive. Well, it's more complicated for second order conditions. And I could teach you it. I just sort of think, nah, maybe not for Econ 403. Because, it's just not important enough for you as a part of the undergraduate curriculum in the economics major to study this. But if you are at all interested, you could ask me or look at a reference book or something, and it'll tell you what they are. It has to do with like other ways to divide up the Hessian matrix. You're still looking at the Hessian matrix, but you're looking at it in a more complicated way. And right now, I just don't think it's important. We can, if I give you a problem with three variables, it'll be in such a way that you can tell that one is something is a max or a min, or I'll just tell you that it's a max or a min. You don't have to prove it to me using second order conditions. Okay, so let's go.
Does our textbook go into more detail about that second order condition, or
which one?
Higher up.
The Sid Sayer textbook?
Yeah, I think the Sid Sater one is the one.
I think perhaps not, or at least, I'm sorry, I'm not sure. My guess is very little is about that, if at all. Whereas I'm sure that the one I'm more familiar with is Alpha Chang and Kevin Wainwright. This one does. It would say exactly what the second order conditions are for any number of choice variables. For lowercase n choice variables, it'll tell you exactly. Second order conditions are sort of weird. It's like, here is a necessary condition. Here is a sufficient condition. Is it the only necessary one? No. Is it the only sufficient one? No. But they are perhaps useful in your life to know a necessary second order condition or a sufficient second order condition for any problem that you're doing. And so, yeah, I would encourage you to look that up or ask me about it if you really want to know more. But if you go into it, let's say you're going to a master's program, PhD program, something with grad school, yeah, this is something that they would teach you. So you would have that in your toolbox at that point in time. But for now, let's just even look at what a problem with three choice variables would look like. Here's one. Let's find a potential maximum for this problem. Could you guys even think of graphing this? What would you even do? There's three input variables into the function, and there would be a fourth variable, which is the output. It would be 4-dimensional if you tried to graph this. The closest you could come to visualizing something like this is like a 3-dimensional heat map, where like you maybe use color for the fourth dimension. Have you ever seen those? Those are weird, but possible. But even that's hard to visualize on anything 2-dimensional. So that's sort of the point. Here's a complicated problem. Mathematically, it's not complicated, actually. Just visually, conceptually, maybe it's more complicated. How would I find the x, the y, and the z that maximizes this function? Well, you guys are well equipped to answer that. Even if you can't visualize it, who cares? What do we do here? I'm going to annotate here. Can you help me annotate and tell me what's the first thing I should write underneath here? Say right here, use the first order.
Find the partial derivatives.
With respect to which one?
X.
Okay. I'll write it like this, fx. Okay, what is it?
It's 4x.
Just positive 4x?
Or negative 4x.
Oh yeah, you saw the negative there. That's correct. Negative 4x, very good.
Plus.
Nothing.
Plus.
This has
Z.
an x in it. Plus what?
Z.
Yes, good job. Plus z.
Minus y.
Minus y.
Minus 6.
Minus 6. And if we want to make it a condition,
Equals 0.
say that it's equal to 0. Very good. Okay, so that's one condition. Obviously, that's not going to be enough to find x, y, and z. It's a relationship between x, y, and z. Luckily, though, we're going to have 3 of these guys, aren't we? We're going to have 3 equations, each one its own condition. But together, these 3 equations will allow us to determine x and y and z. And that's what makes this an interesting problem. I think, Kai did a very, very competent job determining the partial derivative with respect to x. I'm not going to force anybody else to do it. For the other ones, I'll just write it here. Negative 6y. You can tell me if I make a mistake. Y here, no y, no y. Here's a y minus x. And there's a y plus 3 equals 0. Okay. And now how about z? No z, no z, no z. Here's negative 4z squared. That becomes negative 8z. Yeah, that's lined up 2, 3, 4. Very, very convenient. Plus xz, that becomes plus x. What other z's are there? Here's a minus z, that becomes minus 1. This is very solvable, isn't it? Someone's coming into the chat, into the class. I think I've admitted them. Okay, welcome to the class. And we're doing a maximization problem. It says max right here with 3 choice variables. The choice variables are x, y, and z. Notice there is no restrictions on them, meaning that it's not greater than 0 or something. When you see that, it's a little bit of a shortcut here. Maybe I should have, just to use good notation and for completeness, I should have put something like this: x and y and z are elements of the real numbers. That means it can be any number. Not imaginary numbers, though. If we have time, I'd like to talk to you guys about imaginary numbers and some neat things you can do with them. That actually is relevant for economics. You might say, economics is about real things, prices, quantities, cost, and how could you have imaginary numbers that matter? They might matter as the roots of an equation. The root of an equation is imaginary. That says something about the equation itself. Okay. That's later. Sorry, I got distracted. X, Y, and Z, they're all just regular numbers. And how do we solve this? You guys remember Kramer's rule from before the midterm? I'd say this is a good example, a good opportunity to use Kramer's rule if you want. If you don't want to, actually, this would probably be pretty easy to solve without Kramer's rule too. Some of you look like you're writing it and you're trying to solve it. Jordan, are you trying to solve this problem right now?
Yeah, I was chugging away at it.
Nice. I'm curious though. Are you using Kramer's rule or are you using substitution?
I'm doing substitution.
Hey, that's fine. Did you use? I wouldn't use this one though because it's a little bit harder. It has x and y and z. But either of these lower two would be easy to substitute to find one in terms of the other. In fact, did you do that here with x?
Yeah, I solved for x in terms of z.
X in terms of z. Oh, you do that for this last one. Say x equals.
Yeah, for that last one.
X. You get x equals 1 plus 8z, right?
Yeah.
And then you plug that in anywhere you want. You can plug that up here. You can find. Oh, wait a second. Here you can find x in terms of y, and then y in terms of z. And then you could plug everything in here with all x in terms of z, and y in terms of z, and then solve for z. You could do that. Is that what you were doing?
Yeah, that's
How far are you, by the way? What have you learned so far?
I've almost got z.
Okay, go ahead. What do you have so far?
I had only gotten to the part where I had plugged that x, the one I solved for x into
Okay.
the partial derivative for y.
Okay.
Working on.
So you haven't actually substituted into this last one. You're going to have to use this one.
No, I haven't gotten that far yet.
Okay. Do you want to do it? Should we do it together?
Not particularly.
Oh, okay. But this will reward you for having worked so much on it already that you could get the answer. And maybe your answer would be faster than using Kramer's rule. That would be another triumph of substitution. I have to say it would be harder if there was an x and a y and a z in here, wouldn't it? Because then you wouldn't have this really quick substitution. Like you can arrive at this really quickly. You can arrive at here x equals 3 minus 6y. You can get that really quickly. You can put these two together and get y in terms of z really quickly. And therefore, maybe substitution is the best way to solve this. Is it? Let's do it. What do we get? What do we get when we set these two things to each other? We get let's subtract this equation from this equation. When you get 0 equals 2 minus 6y minus 8z. I don't know if that was the best way to do it, but it's fair to do. And if we want to solve y in terms of z, what do we get? Move the 6y over here and divide by 6. We get y equals like 2 minus 8z over 6. I'm sorry, my handwriting is getting worse as I. There is a lot of pollen in Richmond, Virginia. If you hadn't noticed, at least out here in the suburbs of Chesterfield County, there is pollen everywhere. Everybody's sneezing. Okay, so we have y in terms of z, x in terms of z. We could plug those into there and solve for z. But I'm like running out of space. Let's do it. I'm going to do it with my paper and pencil here. Negative 4 times x, whereas x is 1 plus 8z, plus z minus y, where y is actually 2 minus 8z over 6. This is not going to be a nice even round number. I apologize for that. Minus 6 equals 0. Well, I have a way to solve for z now. This is not pretty. Plus z minus 1/3 minus plus 8z over 6 is 4z over 3. What do you get? Let's move all the constants over to the right side, and you get negative 10 1/3. I get 31/3 on the right hand side, and all the z's stay on the left. Get 1 plus 4/3 is 7/3 minus 32. That's an ugly number. 7/3 minus 32/3, which is the same as 96/3. 7 minus 96 is negative 89/3. Z equals 31 over 3. So multiply by 3 both sides, divide by negative 89. I get z equals 31 over 89, negative 31 over 89. Did anybody get something like that?
That's what I got.
Oh, you got the same thing. Good job, Kai. That's confirmation.
I kind of did it in a different way, but I got the
Hey, but
same thing.
that's even better. If we did it a different way to get the same answer, z equals negative 31 over 89. I don't think you can simplify that. What is x? X is 1 plus 8 times that, which I don't even know how to calculate that. It's going to be a big old nasty thing. 8 times 31 is 248. But it's 1 plus that. So it's like 89 minus 248 over 89 minus 248 all over 89, whatever that is. It's another negative number. And we can put stars here. At the very least, we would suspect that these are things that satisfy the first order conditions and therefore might be a solution. Like I said, I'm not going to make you guys use second order conditions for any problem that has more than 2 choice variables. So okay, just like here, you just find a potential maximum. That's all I'm asking you to find. Y star, 2 minus 8z over 6. Geez, I don't even know if I want to do that. What do you guys think? It's like 1/3 minus 4/3 z, where z is 31 over 89. I don't know, just you could always plug that in. And the 2 minuses should make this a plus. So y should be positive, but x and z should be negative, I think. And that's effectively our answer. I didn't actually calculate it this way, but we did it. We solved example 3. And who cares that there were 3 choice variables? If there had been 4 choice variables, it would have been very annoying, but we could still solve that problem. Then there would be 4 first order conditions and 4 equations, and we know we can solve a system of equations. If there's as many equations as there are unknown variables, we should be able to solve it, or we should be able to find that they contradict each other, in which case there's no solution, or they're sort of redundant, in which case there are multiple solutions or infinite solutions. But oftentimes that's not the case. There'll be one unique solution. Certainly if it's linear, I should say, right? If all these equations are linear, then the only possibilities are a unique solution, no solution, or infinite. And in fact, you can tell that by the determinant of the matrix A in this. What do you guys think that is, though? If you wrote this as AX equals D, do you mind if we do that now instead? Like think, okay, well, here's a different way to do this. Let's write this AX equals D. A is going to be a matrix of the coefficients of these linear terms, but I sort of want to rank them in X, Y, Z. It's alphabetical order. It would make sense to do that, right? So when I come up with these coefficients, I'm going to say, first, the one on X is -4. The one on y is -1. One on z is 1. Then the next line is for x is -1. For y is -6. For z, it's 0 because there's no zeros here. Okay, and now f of z for x is 1. For y is 0 because there's no y's. For z is -8. This is a matrix of the coefficients of this system of first order conditions. I would multiply that by x, y, and z. And I would get not a bunch of zeros. I can't just say this equals a bunch of zeros. Don't get fooled by these zeros here. There's a 0 there and there and there. Those aren't actually the correct elements of this final matrix. We actually need to see what constants would be left over on the other side of the first order condition if we had moved it there. So this -6 here actually becomes a +6. And that's what belongs here if we were to write it this way. This 3 becomes a -3. And this 1 becomes a +1. So this is actually the way to write this system of equations in a way that could use Cramer's rule. And just a reminder what Cramer's rule is: to solve for x, you take the determinant of this matrix where the first row is replaced by 6, -3, and 1, find that determinant. I'm sure that's whatever this numerator is. And you divide by the determinant of the original matrix. I'm sure that's 89. Right? But that's what you'd get. You get the same answer doing it that way. And the reason I wanted to do this is not just because I wanted to give you more practice doing Cramer's rule or seeing Cramer's rule, even if I'm not going to make us do it. You're seeing it again. It's because I want to relate this matrix here. Let me do it in red or something. This matrix here, there's something special about it too. What do you think? Is this like matrix A, nothing special about it? We know this matrix by another name. What name is it? No answers? Right now, the thing I've circled in red is a matrix of the coefficients of the linear terms of the first order conditions of this maximization problem. A lot of words to describe that matrix in red. There is a much faster, more compact way to say it that's relevant for this class. Do you know what else this matrix is called? Nobody knows. No guesses? You have a guess, don't you? No, you don't have a guess. It's the Hessian matrix. It's the Hessian matrix of the objective function. Is that like mind blown? Like, wait, why is that the Hessian matrix? I'll tell you why the Hessian matrix is. See fx, if you were to take the derivative of fx again, what would you get? -4. That's what's here, this -4, because it's linear. The coefficient of the linear term of x is also the second order partial derivative with respect to x. What about fxy? Fxy is -1 for exactly the same reason as the coefficient on the y linear term is -1. That's why fxy is -1. For the same reason that the coefficient here on this linear term for z is 1, that's why fxz would be 1. So these terms here, -4, -1, 1, 1, 6, all of these terms are exactly what you would get if you were looking for the second order partial derivatives of f. So it just happens to be in any problem like this, where it's the highest degree in the polynomial is second order. You don't see anything cubed, and you don't see anything where like you have a square times a linear or 3 linear terms multiplied together. Actually, that I think would be okay, maybe not. No, well, you definitely have this property that if you're looking at the matrix of the matrix that you would generate to solve using Kramer's rule, that's the same as the Hessian matrix. And so maybe that says a little bit about, when can this be solved? Well, certainly the determinant of the Hessian matrix should not be 0. If it's 0, it can't be solved. You can already just sort of, I'm almost like I'm dancing around the connection between the second order conditions here and the first order conditions, but there are some, and because I'm not really teaching you the more complicated version of the second order conditions, I don't think you're responsible for it. But I do think it's nice to make this connection that, hey, we weren't looking for the Hessian matrix, but there it is. While solving for the first order conditions, for the potential maximum of this problem, we also generated the Hessian matrix. And we calculated the determinant of it, and it's this number here in the denominator that keeps popping up, 89, which we got using substitution. Okay. All right, so if I asked you a problem that had this 3 choice variables, I think you guys could do it. You could either use Kramer's rule, or you could use substitution. It's really up to you. Look at the problem and see which one would be the easiest one to do in that case. Here's the answer written out on the PDF. That's exactly what we had, I believe. The system of first order conditions becomes this: AX equals D. That's what we did. And then, it's not quite 89 here. It's negative 178. But you realize that's 89 times 2. So it turns out that because all of these numerators were divisible by 2, that's why we saw 89 in the denominator. It was simplified. So I was wrong. It wasn't the determinant of the Hessian matrix, or A, was not negative 89. It was negative 178. But we have potential maxima at this point. I won't make you prove it, of course. But notice that the matrix A in this example happens to be the Hessian matrix of the objective function. When does this happen? I think I answered this question to you before. It doesn't always happen, but it happens when the objective function is no more complicated than a second order polynomial. And just real quick, if you were to think of it as a cubic, if this were instead of negative 2x squared, but negative 2x cubed, what would happen is then there would be, even in the second order partial derivative, there would be some x's in there. And it wouldn't be so simple as this sort of negative 4 times x in the first order condition. There would be like an x squared in the first order condition, and therefore you couldn't do this. So I think that's good for this example. Do you guys have any questions about that? That's probably all we can need to say about problems without any constraints, which is good, because the real interesting stuff is when you start to have constraints, which says you're not just allowed to pick any old x, y, and z, or x and y. Let's start first with just x and y. You can't just pick any x and y. There's some constraint that's forcing you to choose only certain x and y. And I have some examples of that I'd like to go over with you. And that's exit out of this. I've learned this is F. I want it's also on Blackboard now under, I call it Lagrange multipliers and constrained optimization. So we're gonna start just talking about constrained optimization, and then we'll get to this point where we need to use Lagrange multipliers to solve these problems. Maybe some of you have had Lagrange multipliers before, maybe some of you haven't, but I think I can teach it to you, whether or not you've seen it before. It's something you can learn. Okay, first let's talk about constrained optimization. And I've already spoken about trade-offs, that I can only have so much X or so much Y, and I have to choose between them. That's already speaking of it in terms of a constraint. If I get some X, I have to give up some Y. Let's talk about examples of a budget, of a constraint. The first one and most obvious is a budget constraint, which is anytime you're faced with this problem, you're a consumer and the total expenditure, that's how much money you spend, of this consumer is constrained by how much income, how much money you have. Of course, you can't, in these models, you can't spend more money than you have. And then the trade-off there is buying one good instead of another along the budget line. That's a constraint optimization problem. Another example is a production possibility frontier. This is more of a macroeconomic concept that says the total amount of goods produced by a country, not just a person or a business, but the whole country, is constrained by the production capacity of the country. And the trade-off is producing one type of good instead of another along the PPF. You could always produce somewhere along the production possibility frontier of the country, but how much of each one, that's up to you. That's what constrained optimization problem might ask. I'm gonna do a little bit too much glare. That's better. And finally, a firm might have a production function, which says, in order to produce a certain level of output, you need, you have a constraint that you have to produce at least this level of output, but you can change the way the inputs that you use to produce it. And this is like McDonald's. They want to be able to serve 100 customers per hour. Maybe that's a lot. I don't know. They serve a lot of customers per hour. They could do it with humans at the cash registers. They used to be cash registers. Now they're just computers with plugging in your order. Or they could do it with a touch screen. They could install some touch screens, and you walk into the store and press in your order. Maybe you even pay there at the machine, and you have very limited interaction with people. Those are two different ways to produce the outcome that they want, which is get you your food and get you out of there so that they can serve 100 people every hour. Maybe I'm overestimating. Maybe it's more like 20 people an hour. I don't know how many people walk into a McDonald's. But that's an example of constrained optimization. Maybe we didn't think of it that way. Maybe we thought it was just McDonald's is just doing whatever it has to do to serve us. That's what it'll do. There's no problem. Actually, there is a problem. Even behind the scenes, there's somebody out there thinking, what are the different ways I could produce this food for you, create it and serve it to you in a way that's pleasing to you. We also have to keep the floors clean and the bathrooms clean and the tables wiped down. And the food has to be prepared in a safe way. That all of that, it goes into the production of the food. But there's a choice behind the production, which is what's the best way to produce it. And sometimes it's a trade-off between capital and labor. In fact, the reason I picked McDonald's is because I'm aware that a lot of them have already switched from human, I don't know what you call it, register. This is the person that you talk to at a cash register. What do you call them? There's a word for this type of person.
Cashier.
Cashier. I think that's a great word for him. Yes, they used to be human cashiers at every restaurant, at least every fast food restaurant you'd go to, and now some have transitioned to touchscreens where you don't have cashiers. Okay. I would like you to think of that as, oh yeah, that is kind of a constrained optimization problem. What's the constraint? The constraint is that they have to produce the food for you. If they want to make money, they got to be able to serve you this food in a reasonable amount of time, but they can still think about how to do it. Okay. Let's go on. First example I want to give you guys is consumer theory. It's the simplest example. And you know what? I'm even going to ignore prices. Something that's very fundamentally a part of consumer theory is like, what are the prices of these goods? I'm going to ignore them and just focus on dollars spent. In other words, F is the amount of dollars you spend on food. S is the amount of dollars you spend on shelter. So implicitly, there's a price for food and there's a price for shelter. And the higher the price of food, maybe the less food you spend. But I'm sort of baking all of this into just one number, which is F, the total amount of food you spend. And the constraint in this case would be F plus S is less than or equal to M, where M is the total amount of money you have, and you can spend it either on food or shelter, but you can't spend more on food and shelter than you have. We're assuming you can't, there are such a things as credit cards. You could borrow money, but you couldn't borrow money every single month, right? That wouldn't be sustainable. If your income was $1,000 a month, you spent $800 on rent and $500 on food, that just would be a recipe for disaster. You couldn't do that. You couldn't live like that. Okay, so that's what the budget constraint comes from. What if there's no savings in the model? Okay, this is an even simpler model. You have no reason to save. We'll change this later, by the way. But for right now, let's say there's no prices. There's no reason to save. What does this mean? It means F plus S should be equal to M. And this is almost like a behavioral assumption right now. Why? Because you wouldn't choose to spend anything less than all of your money. Assuming that you get some utility, some satisfaction out of both food and out of shelter. When I say shelter, I mean like rent. Do you rent a 1-bedroom apartment? Do you rent a 2-bedroom apartment? Do you buy a house? Do you, have a 1-bedroom apartment that with 3 roommates? I've had roommates before, back when I was a poor graduate student. It's kind of nicer to live on your own if you can, but it saves a lot of money to have roommates. So that's you think of that as all going into your decision. How much do I spend on shelter? It's like, what kind of house or apartment do I live in? Okay, so all of this is to say, it boils down to this one equation, F plus S equals M. And that equation is fundamentally a constraint on how much food and shelter you can buy. You can choose. That's what we need. Okay, we're not done. Oh, by the way, you could write this as a budget line. If this axis is how much you spend on food, this axis is how much you spend on shelter. I've implied that the slope here should be 1 because there are no prices in this model. So it's this blue line is all the different combinations of food and shelter that you could choose. You have to choose somewhere on this blue line. Okay. Now let's talk about the utility that you get from consuming. In economics, we use utility functions not because we think that they reveal something about your true level of happiness or anything like that. We're not that foolish. We don't think that's what it means. We merely think that it represents your preferences in such a way that you will always prefer an outcome with a higher utility over an outcome with a lower utility. As long as that's the case, that's all we really want as economists for your utility function. You might say, well, don't you need to know exactly how much happier I am with this particular bundle than this particular bundle? Not really. I mean, sure, you can do quantitative things with utility functions, but those are always a little, you got to take this with a grain of salt a little bit. Mostly what utility functions are, it's just a representation of preferences. And in this case, I want to make it really simple, just F times S. How much utility do I get from consuming F units of F and S units of S? You just multiply them together. Where actually this is the dollars that you spend. So if you spend $500 on food per month and $500 on shelter per month, I would have to multiply 500 times 500. That would give me utility of that particular combination. You might say, isn't shelter, shouldn't I be spending more money on shelter than food? And I would agree with you. Probably, I think. I spend more on I have a house and I have a mortgage, and I'm pretty sure the mortgage is more than the food per month. But if not, then man, we're spending a lot of money on food. But maybe. We do like to buy nice food sometimes. Let's talk about utility functions with indifference curves. And just as a reminder, probably most of you got a text. Utility functions are give rise, we should say, they give rise to indifference curves, the set of points that give rise to the same utility. That's just called an indifference curve. And it's actually an explicit function of one good in terms of the other, given the implicit function. Hey, we've talked about implicit functions in here. I kind of wanted to do this as another way to connect with the implicit function theorem that we've talked about. And that's to say, this is actually u of f of s equals u bar is an example of an implicit function. Let me say a little bit more about it right now. It says, whatever amount of food I have, whatever amount of shelter I have that I'm consuming, the utility that I get from that is equal to some constant number u bar. And so if f were to change and s were to change, this equation would still hold, where the utility I get from however amount of food and however amount of shelter I'm consuming is constant u bar. That's an implicit function. It's also the definition of an indifference curve. So let me review that for people again. An indifference curve is defined to be all of the points that give you the same utility. Well, that's what u bar is. U bar is a constant level of utility. Any combination of f and s that gives me that utility defines the indifference curve. So that's an indifference curve. Okay, this is all just to talk about this example of optimization. So here is the consumer choice problem. Let's maximize utility subject to the budget constraint. You know, before, our problems would have just ended there, right? Maximize f and s, and the objective function is f times s. That would have been the end of the problem if it was the previous chapter, which is unconstrained optimization problems. The difference now is that we add this phrase, clause, which is that we're not just maximizing f times s unconditionally, we're maximizing f times s such that f plus s equals m. That's called a budget constraint or a constraint. Given this constraint, utility will be maximized when the consumer chooses a point on the budget line that is tangent to a difference curve. Okay, this is not something new to my class. This is something you would have learned in a microeconomic theory class already. What I would like to do in this class is show you how that thing that you've already learned in another class is equivalent to some of the techniques you've already learned in this class, like the implicit function theorem, corollary, and a new method, which maybe you haven't seen, maybe you have, which is called the method of Lagrange multipliers. So there's like 3 ways to think about this problem, and we'll go through them now. I think we have time. It's 1:25, so we have some time. Okay, here is a drawing I have of the budget line with indifference curve. The red curve is the indifference curve. These are all the points that give you the same level of utility, a particular utility, and the blue line is the budget line. And we all sort of know already that there's this point here, right? You know, should I do black? There's something special about this point. It's called the point where it's tangent, where this curve is tangent to this line. It's got to maximize our utility. We know it does. There's no way to get a higher level of utility. Utility is higher this way. If I were on a higher indifference curve, it wouldn't touch the blue line, and that's bad. If I were on a lower indifference curve, it would touch the blue line 2 places, and that's bad too, because I could do better by going up and to the right. So it's only this unique point here where the red curve intersects, not just intersects, but is tangent to the blue budget line that would maximize our utility. We knew that already. What I want to do now is see it in mathematical terms in this class. All right, here are 3 ways to solve this problem. Even though we already know the answer, quote unquote, it's that point where they intersect, but here's way 3 ways to solve. Use the implicit function theorem corollary to get the slope of the indifference curve, set it equal to the slope of the budget line, and plug back into the budget line to get optimal S and F. Do that. Another way, use the budget line as a way to substitute. Substitution is always it can be a very useful method for solving a problem. You can always look for ways to use substitution to make your problem easier. Simplify your problem, and then it'll make it easier to find the answer. I really recommend that if possible. So you could do that. You could eliminate F from the maximization problem, and then it changes the problem from a constrained maximization problem to an unconstrained maximization problem, because you've substituted away the constraint. I don't know if that makes any sense. Hopefully it'll make sense. You take a constrained maximization problem, you substitute one of the variables in terms of the other using the constraint, and then it becomes an unconstrained maximization problem, which you already know how to solve. So this second method here, number 2, is kind of a way for you to turn something hard to solve into something easy to solve, and then just solve it. And I'm pretty much okay with you doing that unless I specifically ask you to use method 3. And this method 3 is probably the one that's the newest for everybody. And that's the method of Lagrange multipliers. The good news about Lagrange multipliers, it can be used to solve any constrained optimization problem, even the ones where you can't substitute. Maybe there's number 2 is great if you can use substitution, but there might be some cases where you can't, like, sine of x squared is just not something you can't, I don't know, that's a bad example, but there are certain equations which just don't lend themselves to substitution. Okay. Let's look at all 3 of these if we have time, if you don't mind. I think I'm going to do the first one first. That's why I numbered them this way, right? How would you use the implicit function theorem corollary to solve this problem? Okay, I'm expressing this to you in terms of a question you could help me answer. The first thing I'm saying is, here is that formula. It used to be u fs equals u bar. But remember, for implicit functions, we always move everything over to the left side and say it's equal to 0. So all I did was move the u bar to the left and said it's equal to 0. Now I want to know, what is ds df? Do you guys remember how to use the IFTC for this? What is it equal to? Equal to, let's be a little bit clear here. The bad news is we've already used capital F for food, which normally that's what I would call this entire function. I would just call it capital F, but that's already being used. Should we use a different letter? Often G. When F is not available, you use G. So this whole thing here on the left side, we're going to call that G of what? Well, actually, it's just of F and S. And how do I know that it's just a function of F and S? Well, because this u bar is a constant, it's not a variable, and this u is a function. It's a function. It's not a variable. So really, this whole left-hand side is like equal to G of F and S. So what is ds df? Let's use the implicit function theorem corollary. Remember what it is? Am I willing to tell me? Remember what you do? You flip and you add a negative. I just asked you about this in like 2 quizzes ago. Was it a quiz or just homework? Yeah, 2 quizzes ago. So you flip. What does that mean? Like the S becomes down here, and this S is now what I'm taking the derivative with respect to of the entire thing, where here I'm just calling it G. So it's kind of like this is GS over GF. I flipped the S and the F. And I also need a negative sign here. It doesn't matter if I put it on the top or bottom, put it there. How about that? Do you agree? Do you see how I got that? I just applied the implicit function theorem corollary. Something we've already learned. I just wanted to find this relationship here, ds df. Okay, it's negative whatever the derivative of this top is with respect to f, divided by whatever the derivative of this top is with respect to s. Okay. Let's actually do a little bit better to figure out what is the derivative of this top with respect to f. Well, it doesn't have anything here. It's really just the derivative of u with respect to f. That's also known as the marginal utility of f, because the partial derivative of utility with respect to one of the input variables is by definition the marginal utility. So I could just call this the marginal utility of f. If I dropped the m and just, that would be okay too, because we already know that the marginal, these little subscripts refer to partial derivatives, so it would also be the same. But that's what we have. That is the derivative of s with respect to f, which also happens to be the slope of the indifference curve. I mean, like, let me go back up. Oops. No, it's okay if I leave it here. The slope of this indifference curve is it's rise over run, where rise is shelter, run is food. That's ds df, and we've just solved for it. It's negative muf over mus. You can argue we didn't need the IFTC to do that, but I just used it because we've had it already in the class. Maybe I should delete this stuff. Oh yeah, wait a second. We know what UFS is. We know what UFS is. It is f times s. Let me write that here too. U of f comma s equals f times s. That was an assumption of the problem, by the way. It's not written anywhere on this slide, but it was given to us that u f of s equals f times s. So we can actually calculate the marginal utility of f as just s, negative s, and the marginal utility of s is f. Is this right? Yeah. This is, I'm sorry, let me get rid of my drawings. Okay, so this is what I had annotated, written out in a little bit nicer way to see it. This is just these are the partial derivatives. So we get this ds over df is equal to negative sf. Okay, that's the slope of the indifference curve at this point. How were we using this to solve the problem? Well, we knew at the solution, the slope of the indifference curve is equal to the slope of the budget line. Once again, that comes from this picture. The slope of this red line is equal to the slope of this blue line. What's the slope of the blue line? It's 1, because it's defined to be equal to 1. So because the budget line has a slope of, well, sorry, -1. It's not +1, it's -1. So the solution will be at the point on the budget line, f plus s equals m, where ds over ds df is equal to -1. So this is the slope of the budget line. It should be equal. Sorry, this is the slope of the indifference curve, and it should be equal to the slope of the budget line, which is -1. We calculated what ds df was. It was negative s over f. And if I solve this for, remove the negative ones, multiply both sides by f, I get f equals s. And okay, so how do I solve this problem? How do I continue on with the solution of this problem? I would take this f equals s and insert it into this budget equation. In other words, replace s with f in the budget equation. Every time you see an s, replace it with f, because that's this condition we found, f equals s. Almost like a first order condition here, right? This is, we haven't solved it yet, but we at least know this condition, f equals s, is true. Plugging that into our constraint is really is the right thing to do. To solve a problem, any problem like this, if you get something like a first order condition, like f equals s, and you plug that into the constraint, like f plus s equals m, you're very likely to get the answer. So instead of f plus s equals m, I get f plus f equals m, or f equals m over 2, or s equals m over 2. In other words, I split my money exactly halfway. Half of my money I'll spend on food, the other half I'll spend on shelter. Remember, this is a solution. Just because we have m's here, that doesn't, you might say, well, we haven't actually solved it because we don't know what m is. Actually, yes, it is a solution because m is exogenous, not a choice variable. So it's totally fine to give your answer in terms of exogenous variables. It's not okay to give your answer in terms of other choice variables like this. Like if you answered this question by saying f equals s, and that's your answer, that would not be right. That would be incorrect. It would be incomplete. You know, partial credit, yes. But the full answer to this problem would be something like this. How much do I spend on food? Whatever m is divided by 2. How much do I spend on shelter? Whatever m is divided by 2. And that is the solution to this consumer choice problem. And we got it just using what we know about this budget line and this indifference curve. And the only real reason it used the implicit function theorem corollary was to get the slope of the indifference curve. That's really all we did it for. Okay. The rest of it was also substitution. So here's an even faster way using substitution. If we had just looked at the problem and said, okay, s plus f equals m, that's the budget constraint. If I use that to solve for f in terms of s, I would get this, f equals m minus s. And then I would replace that into my objective function. So really method 1 and method 2 are very similar, except the order in which you do it is different. In method 1, we looked at finding some first order condition and then plugging that into the constraint. Whereas in method 2, I'm looking at the constraint, I'm solving one variable in terms of the other using the constraint, and then I'm plugging that into the objective function, and then I'm maximizing. So what would that be in this problem? If I know that f is equal to m minus s, and I replace that with the f in the objective function. Remember, this used to be maximize over f and s of f times s. So now it just says, forget about f. There is no more f. I'm only going to maximize s times the quantity m minus s, where I've replaced f with m minus s. This is just a quadratic function in s. I kind of wish I had written that out a little bit more. Let me do it now. You know, what is this actually equal to? ms minus s squared, right? So now we have a choice, only one choice variable. We went from having a problem with 2 choice variables to a problem with 1 choice variable. How do I solve a problem with 1 choice variable? Just take the derivative of it. ms becomes m, and negative s squared becomes negative 2s. I solve for that, I get s equals m over 2. And then I plug s equals m over 2 back into here to get f equals also m over 2. So that's another way. It's actually much faster in this way to solve this problem. Oh boy, I only have 5 minutes left. Dang. So the bad news is these 2 methods, 1 and 2, are not the ways I want to teach you. The thing I would like you to learn for this class is a third way, and it's called the method of Lagrange multipliers. And it's not because I think it's faster in this problem. Of course not. I think the fastest way to solve this example would be method 2. This sort of substitution, single variable optimization problem, bam, you're done. But there's going to be problems out there where you just can't do that. There maybe is no good way to solve for f in terms of s, you know, in which case you couldn't substitute it in. But the problem could still be pretty easily solved using this method, method 3, Lagrange multipliers. And I just don't know if I have enough time to go through a full example of Lagrange multipliers. Maybe I should just break here and give you like an overview and say this is what we'll do Thursday. By the way, have any of you already learned how to use Lagrange multipliers? No? Okay. At least no one's willing to say that they have. It's not that hard because a Lagrange multiplier is ultimately just a variable. It's like you're adding, so you're taking a problem like this one with two choice variables. Where's the problem again? I want to see the problem. Here's the problem. So here's a problem with like two, that's not what I wanted. Two choice variables. And what the method of Lagrange multiplier says, I'm going to add a third variable. And the third variable I add, it's actually going to fundamentally change what I'm maximizing to. So I'm not just maximizing FS. I'm going to maximize FS plus something that is ultimately equal to 0. And because I'm maximizing f of s plus something which is ultimately equal to 0, it means I'm not really changing the solution. Whatever maximizes this new thing will also be a maximum for fs. So here's the new thing that you're going to maximize is not just fs, but fs plus lambda times m, that's supposed to be an m, minus f minus s. And you might say, well, why? So I've added a new variable, lambda. I'm going to be able to choose f, I'm going to choose s, I'm going to be able to choose lambda. But I'm still more or less looking for how to maximize this in a particular way. I haven't changed the fact that I'm still looking for something that maximizes f times s. Because if you think about this part of it, this part I'm highlighted in red, it should always be equal to 0. You might even think, how could it possibly matter whether I include that or not? Because it's always equal to 0, because m is always equal to f plus s. So m minus f minus s is always equal to 0. So I'm just taking f times s plus something which is equal to 0. Who cares about it? Well, it will change the first order conditions, won't it? And that's exactly the point. Lagrange, the mathematician who described this method, did it because it's a way to internalize this constraint into the maximization problem. It means when I'm looking at first order conditions for the maximization problem, I'm not just going to be thinking about what happens to the objective function f of s. Like as I change f, like let's say I'm considering different values of f. It's going to have this effect on the objective function, but it's also going to have this effect on this part of the function. In the first order condition, it's going to be there because if I take the derivative with respect to f, there's an f. There's going to be a lambda in there. And it's a way to internalize the trade-off of choosing either f or s because, as you can see, changing f will mean I also have to change s in order to keep this equal to 0. All right. I want to give you the specific example on Thursday. But that's my preview of what the method of Lagrange multipliers is. So you can look it up and get started on this problem if you want. But if not, I'll do it for everybody on Thursday. I think that's about my time. I want to have another homework for this class, but I haven't posted it yet. So I'm thinking it is not going to be due on Thursday. It'll have to be due next Tuesday because I haven't posted it yet. So I don't want it to be due in a class where I haven't posted it. So expect the next homework assignment to be due like a week from today, I would imagine. And I'll ask you maybe like a three choice variable maximization problem, unconstrained, and something kind of simple where there is a constraint too. I could give you like one of each of those types of problems. I think that would be reasonable. You guys have any questions about this this stuff? Feel pretty good. Yeah, hopefully it's more of the same. You've already done optimization problems. This is one new aspect of them, and that's what if there's a constraint? And there's many different ways to deal with the constraint, often involving substitution. But I want you to know this way, Lagrange multipliers, you'll be able to do it. It's not that much harder than what you already done. So I'll see you guys on Thursday then. Have a good couple of days, and see you later.